It's time for a new section, and we start chapter 4 with extreme values of functions. In this section and in the following videos, we are going to learn about absolute or global extreme values, local or relative extreme values, and finally, how to find extreme values once we've defined them. So this video is going to be about the first of those things, the absolute or global extreme value. So we're going to get some definitions here. We're going to learn what an absolute maximum and an absolute minimum value are. We're going to learn how to use the term global to describe minimums and maximums, and then also about the phrase absolute extrema. We are going to get one big important theorem in this video. It's called the extreme value theorem, abbreviated the EVT, and that's coming along as well. So we begin like this, and it's a big overarching theme of chapter 4. We're going to learn how the derivative is useful to us in describing a function and the behavior of the function. And one of the most useful things we can learn from the derivative of a function is whether the function assumes any maximum or any minimum value on a given interval. So does a function hit a top or highest or largest value, and also does it assume any small value on some given interval? If we learn how to find those values, those y values of the function, then we're going to be able to answer some really important questions. Like, what's the most effective size for a dose of medicine? Or what's the least expensive way to pipe oil from an offshore well to a refinery on the coast? These are type of AP free response questions that we might see later on. So in this section, we're going to learn how to answer questions like those. We begin with a big definition screen. We want to define absolute extreme values, and it goes like this. Let's let f be a function with a domain D. Then f of c, remember, is always a y value. Then f of c is the absolute maximum value on the domain if and only if f of x is less than or equal to f of c for all x in that domain. So this means that all the y values are less than or equal to, which basically means on a graph lower than the maximum y value. So that's a good way then to define an absolute maximum. Say, hey, look at a domain, look at a graph of a function on a particular interval, and then decide for yourself, is there a y value that is greater than, that is higher than all the other y values around it? And then there you have a max. We define a minimum very similarly. Then f of c is an absolute minimum value on the domain D if and only if f of c is greater than or equal to f of x is greater than or equal to f of c for all x in D. In other words, all the y values are greater than or equal to, which means all the y values are higher than the min y value. And that makes sense then why we call it a minimum. So a little further down, absolute maximums and minimums are also called global maximum and minimums, and they're also called absolute extrema. We use extrema because it's the plural of the Latin word extremum. And a lot of times you're going to see that we omit the word absolute or global and just say the maximum or the minimum value. When you see the word the in front of maximum or minimum, usually we're talking about absolute or global maximums and minimums. And we're going to see in example 1 that we see extreme values can occur. This should be at interior points and endpoints of intervals. So here's example 1. On the interval negative pi over 2 to positive pi over 2, and notice this is a closed interval, so we're including the endpoints, f of x equals cosine of x takes on a maximum value of 1, and it does that once, and a minimum value of 0, and it does that twice. So this blue graph is f of x equals cosine of x. So let's take a look at its maximum value. That's the highest point. It's here, and it's when x is equal to 0. Next, it's got minimum values, right? And they occur at both of the endpoints. And in fact, there's a tie for the minimum value. It's here, the minimum value is 0, and it's also here at pi over 2, the minimum value is 0 again. So we have an absolute max and an absolute min on this closed interval. Next, let's look at g of x equals sine of x. So that is the red graph. So this is g of x equals the sine of x. And it has a maximum value on its far right endpoint. That maximum is 1, and it occurs at x equals pi over 2. Its minimum value is at its left endpoint. This is the minimum value of -1, and it occurs at -pi over 2. So that's kind of a graphical understanding of extreme values. Let's try exercise 1 from the textbook. So we want to just find the extreme values and where they occur. So for number 1, the maximum value, its highest point, its greatest y value occurs right here. Let's do this in blue. Let's call it the absolute max is 2. And where does it occur? It occurs at x equals 0. So x equals 0 is where the absolute maximum is. The absolute maximum value is 2. What about minimum? Well, I see 2 places, I believe, where there's a minimum value. It's at -2 and it's at +2. And that minimum value is the y, of course, and it's 0. So absolute min is 0. Remember, it's the y value. And it occurs at both x equals -2 and x equals 2. So moving on, then, let's take a look at what happens if we consider a different type of interval other than one that is closed. So the absolute extreme of the following functions on their domains can be seen in the figure to the right. This is directly from your book in figure 4.2. It's chapter 4, section 1, figure 4.2. And we have the graph of y equals x squared a few different times, but notice that the domain changes for each one of them. So in part A, we're looking at a domain of -infinity to infinity. For part B, a closed interval from 0 to 2. Part C, an interval of 0 to 2, but we're open on the 0 and closed on the 2. And then finally, an open interval from 0 to 2 on part D. So the function rule for part A is y equals x squared. The domain is -infinity to +infinity. And are there any absolute extrema here? Well, I see an absolute extrema, a minimum. I have an absolute minimum value I'm sure of, and that is a value of 0, and it occurs at x equals 1. Absolute minimum is 0 at x equals 0. I guess I said 1 while ago. It's at x equals 0. All right, let's move on to part B. And we have a closed interval from 0 to 2. So these are shaded in dots or closed dots to say, yes, we have a point at the end of each side, the left and right endpoints of this interval. So the function rule is still the same, y equals x squared. The domain this time is closed from 0 to 2. And the absolute extrema here, I think we have an absolute minimum and a maximum. I've got a minimum, same place as part A. Absolute min of, let's try that in equal sign. Absolute min is 0 at x equals 0. And then an absolute max is over here, I think, and that's a value of, well, if it's the function x squared, you plug in a 2, that'd be a 4. 2 squared is 4, and that's at x equals 2. Let's go to part C, where we have the same function rule, y equals x squared. This time the domain is open on the left and closed on the right. So this is an open circle here, and then we kind of curve up to a closed circle. So because the left side of this interval is open, this function really does not ever hit the value of 0 inside the interval. We get closer and closer and closer to 0, but we never get there. And so there's really never a way to pick out a minimum value here, because if I say, oh, well, the minimum value is 0.1, someone else could say, no, it's 0.01. And then another person could come in and say, no, it's 0.001. And there's really no way to come up with the absolute minimum, because we can get closer and closer to 0 for eternity. So there's no absolute minimum there, but there is an absolute maximum. Absolute max is 4, and that happens at x equals 2. That's the right side of the interval again. Next, for part D, it's the same function rule, but this time the domain is open on both sides, 0 and 2. And that means we've got an open circle there, and we move to an open circle on the right side. And there's just nothing. There's not a way to reach an absolute minimum. We've discussed that. For the same type of reason, there's no way to reach an absolute maximum, because we never really will get to x equals 2 since we're open on the right side of this interval. And that means the function never actually takes on the value of 4 inside the interval. It just gets closer and closer and closer. And so one person might say, well, the maximum then is 3.9. And someone else says, no, it's 3.99. And then, no, it's 3.999. And we can get closer and closer to a 4, but never hit that value exactly. So we've seen then that absolute extrema can be at the endpoints if this function is on a closed interval, or an inside or an internal point. Here is the next example. This is exercise 3 from your text. Find the extreme values. Bit of a blurry picture. I want you to see here, this is a closed dot at 0, 5, and then down to an open dot here at 2, 0. So looking at this graph, I see an absolute maximum, but I do not see an absolute minimum, because we can get closer and closer to 0 as the value of the function, but never actually hit it. So my answer here is just that there is an absolute maximum value. It is 5, and it occurs at x equals 0. All right, let's move on. And here's the big theorem of our first video. Example 2 shows us that a function might actually fail to have a maximum or a minimum value. And this cannot happen, though, if we look at the function as being continuous on a finite and closed interval. So as long as the interval is closed, and as long as our function is continuous, we're going to have a maximum and minimum value. And that's what the extreme value theorem tells us. If f is a continuous function on a closed interval a to b, this is known as the hypothesis of the theorem, then f has both a maximum value and a minimum value on the interval. This is known as the conclusion. So here's what we want to know about the extreme value theorem, also called the EVT. If you've got a function that's continuous, and it's continuous on a closed interval, meaning the endpoints are included, then you are guaranteed to have both a maximum value and a minimum value on that interval. And we can see here down below the 4 different graphs that each of these functions are continuous on closed intervals from a to b. And we see that the maximum and minimum value can occur in a couple different places. They can be at interior points. Here in the first example, there's the maximum, here's the minimum. The left endpoint and the right endpoint are not absolute maximums or absolute minimums. On the second graph here, we have an absolute maximum at the left endpoint and an absolute minimum at the right endpoint, but there are no absolute maxes or mins, interior points inside the interval. On the third picture, we've got an absolute minimum on the left interval at A, and then the absolute maximum occurs at an interior point, but there's nothing at the right interval. And finally, the opposite's true on the last graph, that we have an absolute minimum at an interior point and an absolute maximum at the right endpoint, but nothing at the left endpoint. So the takeaway here is that if our function's continuous and it's defined on a closed interval, then in that interval we will have both a maximum and minimum value, and the maximum or minimum could occur at the endpoints, but they could occur at interior points as well. That continuity feature of f in the EVT is so essential. Here's a picture below of a function that is defined on a closed interval. This function is defined from 0 to 1, including at 0 and including at 1, but there's no absolute extrema. The reason being is that this function is not continuous. See, we keep going down here. We never actually approach 0, so there's no minimum value. Here, the function continues to rise up, but because this is an open circle, we never actually reach the y value of 1, so there's no maximum value. So we need those two features. We need continuity, and we need it to be defined on a closed interval a to b. So that's the end of the first video. Join me back on the second one.